Today, corrugated tubes. How do they work? Let's get into it. We're doing it live. Here, you see a corrugated tube. Also referred to as whirly tubes because of how you have to whirl them around to make noise. They are little pipes with evenly spaced little grooves on them, and you spin them fast enough, they make distinct pitches. Also, if you blow through them, they whistle. But that only works with the thin ones. Alright, this is all you're getting of me on video for this. I don't really want to show myself on camera. I don't like to, but here you go. Corrugated tube. Small one. And I grab another. Stick them together. Ta-da, they make noise. So unlike other tubes that air might be traveling through with air columns, you need to correct for the corrugation. So in this we've got the pipe itself, got the corrugation, we've got the height, width, the average radius of the pipe, and the pitch. So if I come back to my notes here, this is how we figure out the correction for the pipe, because yeah. So yeah, so when we're calculating the speed of, or not the speed of sound, when we're calculating the excuse me. Oh, yeah, when we're calculating for wavelengths, we have to go a little further outside of the tube, and we have to correct for the corrugation because it'll be slightly off compared to a non-corrugated tube when you're measuring the air columns inside of it. All right. No, we don't want that. We want this. So, trying to figure out how to calculate anything relating to the whirly tubes can be a little confusing. I know. But since the particles are still vibrating in air, if you know the frequency and the space in between the grooves and the speed at which you're spinning it, you can... If you're missing one of those, you can generally find the rest of them. Same way you would find the wavelengths, knowing the speed of sound in air and the frequency or whatnot. Anyway, this is a rumble strip, which functions similarly in how it makes noise when a car goes across it. Because the frequency of this is simply the speed of the car over the spacing between the bumps. Which would give you the frequency that they make when the car's driving over it. And that's kind of like a simplified version of how the whirly tubes themselves work. Pull up the frequency for that here so y'all can see it. Or the frequency is equal to car speed over bump spacing. When it comes to whirly tubes, the pitch doesn't gradually increase when you spin it faster. Only specific frequencies are heard when you reach certain speeds. Now, the reason it does that is because they only make sounds at certain frequencies because as an air column with two ends, it produces standing waves. And only when you have the standing waves does it make the sound. Pull that up here. You just see it's coming outside because it's open to open. So you're correcting for that, and also the corrugation in the whirly tube. So it'd be a little further for the whirly tube. But when there's this showing the fundamental here, when there is a standing wave, that's when we hear noise. So the standing waves show the natural frequencies or overtones of the whirly tube. If it creates the little football pattern, then that's when we know that it's producing a distinct pitch sound, and that's kind of when it does that. That's it's making noise. Specifically, when it does that. If you don't hear a sound, then it's not making a standing wave. If you reach the minimum speed required to make a note with a whirly tube, as long as you're not spinning fast enough to reach the next note, it will continue to play that pitch, even if you're increasing the speed a little bit. So, the frequency that we get for n number of little football shapes is equal to the number of football shapes times the fundamental frequency. So, Fn is the frequency for n number of footballs, n is the number of footballs, and then F1 is the fundamental frequency. So, n equals 1 is the fundamental. N equals 2, twice the fundamental. So, 1 football is the fundamental, 2 footballs, twice the fundamental, 3 footballs, etc., ad infinitum. Let's say we've got this whirly tube here, and it produces a pitch of 249 hertz. When it's spun at the lowest speed it'll play a note at. How do we know if this is the fundamental? Depending on the other information, it may be. But let's say that we're also given that its next overtone is at 332 hertz. Since air columns with both open ends create overtones at whole multiples of the fundamental frequency, wouldn't make sense for 249 to be the fundamental, since the difference between the two is 83 hertz. That must be the fundamental, and 249 hertz is an overtone. Now we're back to the one that I accidentally opened there. So, something seems odd though. If our whirly tube has a fundamental at 83 hertz, it would have another overtone at 166 hertz. But the first frequency we're able to hear is at 249 hertz. which raises a question of wonder of why we can't hear the fundamental frequency. Frank S. Crawford noticed this and decided to run an experiment that's results were published in 1973. In his experiment, he took Whirly tubes at different lengths and figured out the frequencies at which the Whirly tubes started to sing. The result of which being this, which I have to zoom in. Woo! Zoom that in. The column on the far right, the F times Fs, shows the frequency at which the Whirly tubes could first be heard playing a note. The column next to it, to the left, shows the highest frequency at which no note was heard. Now, why is this important? Take a look at the highest value in the no-note column, which is 203 Hz, and the lowest value in the note column, which is 217.5 Hz. This suggests that somewhere in the range lies the minimum fundamental frequency required to actually be able to produce sound. Since our example's fundamental frequency of 83 Hz and its 166 Hz overtone are below that range, the Whirly tube is unable to play those notes when we spin it. The first note we hear is 249 Hz because it's the first overtone present that's higher than that range. The reason ties into turbulence and other things that are far beyond the scope of what we're learning here in class. This video was made possible by the efforts of Jezebel May Sunshine and Natalie Tombach.